to my talk today. I'd like to extend special thanks to Joe and Ben for organising the seminar series and inviting me to give this talk. I can only hope my talk will be as good as the talks that I've already had in this seminar series. So like Joe said, I'll be talking a little bit, but I'll be talking today about what I've been doing for the past 2 years in Chapel Hill, and that is looking at ice quakes at some active ice-covered volcanoes in southern Chile. So later on in the talk, so just to give you a little bit of a rundown about what I'm talking about in this talk, I'll start off with a little bit of background, a bit of a motivation, just explain why am I bothering to study ice quakes at these active volcanoes. And then bulk of this talk will be about what I've been doing at Yaima volcano, with looking at 2 different data sets from 2015 and 2019. And then I'll have a couple of slides later on about the deployment I did at Eureka volcano early this year. And then towards the end, I'm going to talk about where I'm going to go in the future with my work, with a couple of slides about what I've done in Spur volcano in Alaska and what I'm proposing to do in Iceland. So I'll just move on straight onto the background. So why is it important that we monitor ice-covered volcanoes, especially active ice-covered volcanoes? So the presence of ice on a volcano, especially when it's erupting, actually introduces a lot of extra hazards. Probably the most famous of these is explosive interaction between ice and lava. And the classic example that everyone talks about is the Eyjafjallajökull eruption in 2010, which disrupted Europe for several weeks and caused something like 3.3 million euros in economic damage to the aviation industry. And then down on the ground, you also get rapid melting of the ice, which can produce these very destructive lahars, or in Iceland, there can be these glacial outburst floods called Jökulhlaups. I mean, one of the best examples, and probably the saddest examples of this, is the 1985 eruption of Nevada del Ruiz in Colombia, with a lahar there that overwhelmed the town and killed 25,000 people. So these 2 examples can really highlight why it's so important that we really keep a close eye on active ice-covered volcanoes all around the world. And the other thing to remember about these places, they're often very pretty places. So they're high tourism destinations. So for example, Waipuhui volcano in New Zealand is covered, it's got some ski resorts on the flanks and it's in the middle of a national park. So making sure that people can safely evacuate from these volcanoes before an eruption is a key priority. And just like this volcano in Iceland, they also lie directly beneath very busy flight paths. So if these monitoring agencies can give better warnings to the volcanic ash advisory centers around the world about impending eruptions, that's always a bonus. So as many of you might know, seismometry is probably the most widely used tool for tracking activity at volcanoes. If there's any kind of active volcano around the world that is monitored, there's probably at least one seismometer somewhere on or near that volcano. So volcanic earthquakes are generally divided into 2 major types of events. There's the high and the low frequency events. So the high frequency events are dominated by the VT events, the volcanic tectonic events. And you can see a nice couple of examples here. See a couple of nice examples here from Alaska, from Pavlov. And this is essentially the same as larger scale tectonic events. And they're just caused by stress changes due to rising magma beneath the volcano. And then there's the low frequency group of earthquakes, which is much larger, lots of different types of seismic sources occurring in this, and most dominated by these long period events, or LP events. And usually, but not always, these are associated with the movement of fluids beneath the volcano. And these are quite important earthquakes for those who are monitoring volcanoes, because if you get a swarm of these low frequency volcanic seismic events before, then that might hold a new period of eruptive activity. So what about glaciers? What about seismology and glaciers? So actually, cryogenic seismology is not really an active area of research up until the year 2003. And in that year, there was a seminal paper that was published by Ekstrom et al., which documented this quite large seismic event that was located in Greenland. And it was found to be associated with a major calving event from the front of a glacier. ever since then, there's really been an explosion of research into cryoseismology, because people have realized that it actually provides a new way of looking at processes that are happening within the glacier or beneath the glacier, and give us new insights on how the glaciers might behave in the future, particularly in this period of fundamental climate change around the world. A lot of different processes have been identified as major sources of cryogenic seismicity, and these are nicely illustrated in this figure here. So you get iceberg carving from the front of the glacier. These are chunks of ice that are coming off the front of the glacier into a body of water, such as a lake or the ocean. You also get a lot of crevassing within or the surface of the glacier. So you might also see a lot of low frequency tremor from subglacial water flow, as water from melting is flowing beneath the glacier and down slope. And then you also might get some low frequency earthquakes from hydrofracturing. This is where water might flow into and out of cracks within or at the bottom of the glacier. Probably the most important for us is the stick slip motion at the ice rock interface. This is where you might see some friction between the ice and the rock is causing some stick slip motion, some highly repetitive earthquakes. So what happens when, so what can we really learn from these ice quakes? So I kind of alluded to a couple of these things already, but what most important of these is that we can really get an understanding of the long and short-term behavior of glacier velocities. You can also get a better understanding of melting rates. So by tracking, for example, by tracking the number of icebergs that are calving from the front of the glacier, or by tracking the intensity of tremor coming from subglacial water flow. You can also get a better understanding of the properties at or around the source of stick slip motion beneath the glaciers. So for example, you get a nice idea of what's the frictional properties of the subglacial geology. You get an idea of how much water is saturated in the geology. And probably one of the most important is actually understanding of exactly where the water is flowing. And this is really important to know when you want to predict where exactly, for example, a glacier outburst flood might come out in a wide area of a glacier. So what happens when you combine these two fields? So there's only really been a few studies that looked at ice quakes on active volcanoes around the world. And the first of these was actually in the 70s, when some people noticed that what they thought were volcanic earthquakes at Mount St. Helens were actually probably due to the glaciers on the volcanoes. These glaciers were subsequently destroyed by the eruption of Mount St. Helens in 1980. More recent studies have been done in Ecuador, so in Cotopaxi in Ecuador, and Katla in Iceland in 2009, which is a nice figure I've got from here on the left. So what John Sotter et al. Noticed was that they looked at 10 years of seismic data from this particular area of Katla volcano in Iceland. And what they noticed was that they were very strongly repetitive. So you can see some of these earthquakes can be grouped together into these into families of earthquakes that, even though they occur at the same time, they look almost identical. And what they found out was that over 10 years of seismic data at Katla, 12,000 seismic events that were originally classified as volcanic had to be reclassified as coming from the glacier itself. And also more example, another dramatic example, more recent, is from Mount Rainier in Washington, a study that was led by Kate Oldstad and published in 2014. And similar to Katla, what she looked at was over 10 years of seismic data from Mount Rainier. What they found was that there was 150,000 seismic events. And I should clarify that these seismic events were not originally catalogued by the USGS, but they actually found they were too small to really be seen in the original catalogue. But what they concluded was that if these 150,000 seismic events had been seen, they might well have been classified as volcanic, but actually they were coming from stick slip motion beneath at the base of the glaciers and the volcano. So some of the key points that both of these studies in Iceland and in Washington found was that these ice quakes are very strongly repetitive, and they may persist for months to years. And also that more importantly, that these earthquakes will share very similar waveform characteristics to low frequency volcanic earthquakes. And this might be a real problem for anyone who is monitoring ice covered volcanoes around the world, because how would they be able to tell how would they be able to easily tell the difference between what is volcanic and what is glacial? And sometimes you can't really get great locations and depths to be able to really confidently say which is which. So, so this is just a slide just to summarize what the problems I'm trying to tackle in this project is and what the aims of this project is. So really, I want to go down to Chile, when no one's really looked at the ice quakes in detail at the active volcanoes down there. I want to estimate the quantities, locations, and the source mechanisms of the ice quakes down there. And ultimately, what I want to do with this project is I want to develop some kind of criteria that can be used to effectively differentiate what is glacial, what is volcanic, and maybe even develop some kind of automatic software that can be used to classify, automatically differentiate these events. So these are the two active volcanoes I'm looking at in Chile. It's Llaima volcano on the left and it's Villarrica volcano on the right. So these are the two of the most active volcanoes in Chile. And actually Yamin, which is the Chilean version of USGS, is the geological, the government agency of Chile for looking at the geology of Iceland, and looks after OVDAS, which is the observatory, the National Chilean Observatory. They released a list earlier this year of the top 14 highest risk volcanoes in Chile. And as you can see that Villarrica and Llaima are at the top of those lists. So this really emphasizes the need to get a better understanding of what exactly we're seeing in the seismic data from both of these volcanoes. So for those of you who are not familiar with Llaima volcano, it's one of the most active volcanoes in Chile with at least 50 documented historical eruptions in the past 400 years. The last of these eruptions was in 2007, 2009, and you can see a nice photo of this eruption on the right here. And this photo actually really nicely illustrates the kind of eruptive activity you might see at this volcano, where you get strombolian explosions at the summit with a lot of ash being generated. You might get some lava flows going down the flank, and these lava flows might interact with the glaciers which are present on the volcano. And it's actually been calculated that there's been over 14 square kilometers of glacial ice present on this volcano. And then you can see these nice plumes of steam coming off this interaction. And you can also see the lahars coming down the flank of these volcanoes. And I think in this particular event, it was actually flowing towards an area where people can ski on this volcano. So Llaima is actually on the edge, and most of it is within a very popular national park, and it's also directly beneath a very busy flight path where planes from Santiago, the capital of Chile, are flying down to some major cities further south in the country. So that's why OVDAS are keeping a close eye on this volcano. It's such a high-risk volcano. But despite all these glaciers on this volcano, icequakes are actually very rarely reported. So this raises the question: is were they catalogued as volcanic or not? So what I've been looking at are data from 2 deployments on this volcano. The first of these is from 2015, that was deployed in a study that was led by Jonathan Lees, as well as some colleagues from Boise State University. And the aim of this deployment was to carry out some tomography of the volcano, which they published in 2018, in which they found a magma body that was roughly 8 to 13 kilometers depth. So in the next few slides, I'll be talking about what I did for 2015. And then later on, I'll talk about what I did for 2019. And in this case, what I did was I did a small array of broadband seismometers and infrasound microphones to complement what was already deployed there by OVDAS with their permanent network. But before I do that, I want to talk a little bit about what exactly I'm doing with this data. So first off, I have to obviously find the seismic events to decide whether they might be icequakes or volcanic. And what I do is just a very simple multi-station approach where I use an STA-LTA algorithm to scan through each of the seismic stations to find possible seismic events, and then I only select events which are detected on multiple stations. And then the second step here, what I'm doing is I'm taking it back to, I'm really assuming that the glacier seismicity at Llaima are probably of a very repetitive nature. And this is actually based on what was seen at Katna and Mount Rainier volcano. So what I do here is I take every single of these seismic events and I compare them with each other and find those that resemble each other and put them into families. This is like illustrated in this figure here by Berman and West. And I just assign these matching waveforms into families of events. And then I take an extra step just to make sure I didn't miss any events, where I take the median family waveform, also known as a stack, and I take this stack and I scan them through the entire data set just to make sure and find any matching events that were not already detected in the previous steps. So this is what I found for 2015 using these couple just a simple steps. I actually found nearly 5,000 candidate events, and this far outnumbers what was already manually catalogued by OVDAS. And this is to be expected when you're doing something manually versus doing automatic. And from this catalogue, I found over 1,100 repeating seismic events, and these were divided across 11 families across 2 months of data. Only 2 of these events actually match what was originally classified as long period events in OVDAS during this period. The largest family during this period actually contains nearly 400 events, and you can see that plotted in blue at the bottom of this plot. So in this plot here, for those of you not familiar with this kind of plot, is I plotted just essentially every single family as a line, and each dot is the time of an individual event within that family. So you can see the largest family here is actually very persistent throughout the whole period, but some of the other families might start off strongly, but then might taper off, or they might be quite weak at the start and then get stronger and stronger as we go through the period. So for the next few slides, I'm going to focus on what we see in the seismic event for the largest family. So this is an example waveform just from that largest family, and you can see the frequency spectrogram below it here is quite a broadband frequency. I should say that this is recorded at the station that was closest to the glaciers, so this is quite high up at the volcano. So what I wanted to do, one of the first things I wanted to do was, do we see any relation between the size of the seismic events and the time period since the last event in that family? So are we seeing any kind of stress buildup between seismic events in this family? But since we don't really don't really have a good idea of the locations of these families, and you can't really calculate accurate magnitudes, what I'm doing instead is just calculating a pseudo energy. So what I'm doing is taking the envelope of this waveform, so just the highest peak of this waveform, and just taking the integral of that. So just as a comparison between different events in this family, so that's the size of an event. And I plot this against the repose interval since the last event in that family. You can sort of see there's a very weak correlation in the repose interval and the pseudo energy of the subsequent event in this family. So this is indicating there might be some kind of stress buildup in this family. So maybe some kind of shearing is happening at the source of this largest family. And when we try to do this for some of the other families, we do see this in some of the other families as well. So what about location? So location is probably the most important thing if we want to try and differentiate between volcanic and icequakes. But sometimes this might be very difficult, as illustrated by this plot here. So what I've done here is I've taken the first event in the family, plotted it as it was recorded at different stations in order of distance away from the summit of the volcano. So the top here is actually at the summit of the volcano, and at the bottom here is about 15 kilometers away from the volcano. And you can see here that the event itself is actually quite quickly lost into the background noise in the stations. So it's actually very difficult to do locations with individual events in the family. But what we can do, and this is inspired by what was done at Mount Rainier, is we can take advantage of the repeating nature of these families and essentially take a median stack for all these, for the whole family at each individual station, just to get rid of the background noise. And what you can see here are the stacks for every single station. And you can see you're actually getting some nice arrival times that we can start using for getting locations for this particular family. But before I show you the locations of this particular family, I just want to bring your attention to the frequency spectra of the stacked waves in this particular family. So now, if we were to see if the source of this family was to involve any kind of resonance of a fluid-filled crack, for example, you might expect to see shared spectral peaks in all of the stations, but you don't really see this for this particular family. So what we can take away from this is that we're not really seeing any major component of fluid motion for the source of this particular family, or the largest family. And the other thing I want to bring your attention to is we look at the very first few seconds, so the arrival waveforms of these stacks here, which I've plotted in this plot here. And the reason we want to look at this is that if we look at the first motions, essentially, if the ground is moving up or if the ground is moving down in the vertical component at each station, if the first motions is identical at all stations, then you can probably conclude that the motion is isotropic. So essentially the source is moving out or in during the generation of the seismic event. But what we can see is actually there's mixed first motions at all the stations. So there's probably a major component of shear motion happening at the source for this particular family. So here are the locations for the three of the families from which we can get enough arrival times, clear arrival times to do locations. To do locations, what we did is a very basic 3D grid search, where we took a digital elevation model of the volcano, broke it down to 30 by 40 by 40 meter blocks, and essentially asked, okay, which of these blocks best explains the arrival times for the stacks that we get for all the stations around this area. And what we find is that these three locations are actually quite highly clustered around the summit. And you can see these same locations plotted in this satellite image of the summit. So this is the summit vent here. This is where the 2009 eruption occurred from. And you can see that these locations are quite close to, or actually directly beneath, the glaciers near the summit. But I should add a caveat that these locations have very big errors, probably on the order plus or minus 500 meters. Because, well, most importantly, is we don't really have a very good velocity model for this volcano. So we don't really have a good idea of how fast the seismic waves are moving through this for the volcano. And the other thing is that during the stacking process for this family, if there's any kind of slight misorientation in the stacks, this could introduce errors in the arrival times for the stacks. So I would take these locations with a pinch of salt. But what we can do is we can go back to these stacks and we can quite clearly see that there is a move out of these earthquakes away from the summit. So we can be confident that the location for this particular family must be located quite close to the summit. If we move at other families where we didn't really get enough clear arrival times, you can see this particular family here. This is actually first arriving at station Geo here, which is located here on the flank of the volcano there. And you can safely conclude from this particular stacks that this family is probably coming from somewhere in this area, quite close to the terminus of this particular glacier. So I've already published the results of my work on the 2015 data set. And you can see it here in this research article that I published in Volcanica earlier this year. I'll post a link to this paper in the chat box later on at the conclusion of this talk. But I must move on to what I've been doing for the 2019 deployment. So just to remind you, what I wanted to do for this 2019 deployment was to test whether including a small array of broadband seismometers to complement the already deployed, the permanent network of broadband seismometers around the volcano is a better idea than just doing a network of seismometers. And this time, I'm actually doing a greater integration of data from OVDAS, including their seismic catalog. And I've also included some infrasound microphones. So the idea of including infrasound microphones this time was to see whether any of the seismic events could have been generated by something that's happening at the surface of the glaciers. So for example, is there any kind of surface crevassing, or is there any kind of area, particular location where ice is falling off the glaciers, just like they might have seen at Katla volcano. So this is what we see for 2019. We see actually a much larger number of events, but OVDAS have also catalogued a much larger number of events in this time. So it's obviously a more active period of seismicity. And from this catalogue, we see over 2,000 repeating seismic events. And these are divided across 85 families. But I should add that I use a slightly different criteria for the step where I take a stack of each family and scan it through the data. So it's not a surprise to see more families in this 2-month period in comparison to what we saw in 2015. But I did try to replicate what we see in 2015, and I actually found exactly the same number of families. And this time you also see a much larger number of events already catalogued by OVDAS, and it's actually almost a quarter of what OVDAS are cataloguing. And the largest family was also again plotted in blue here, and still again very persistent through the whole study period. So one of the first things I looked at was obviously the infrasound microphones. Do we see any kind of co-seismic arrivals? And the answer is effectively no. So for all of these families, we do not see any obvious acoustic waves that are arriving shortly after the seismic waves. So this particular station was only located less than a kilometer away from the nearest glacier. So you might expect to see an acoustic waves arriving only a few seconds after the seismic waves, but you don't see anything. So this effectively eliminates any kind of surface crevassing or icefall as a possible source for repeating seismicity at Yaima. But one of the nicest things I've noticed for this particular family is that you can actually see these quite clear multiple arrivals happening. And it's, this just means that some of these might be P and S waves, but some of these might also be reflections of some high contrast boundaries within the highly heterogeneous edifice at Yaima. So one of the things I'd like to do next is, can we possibly develop some kind of shallow velocity model using these particular seismic events for Yaima? And in turn, we can get some really nice, much more accurate locations for these events in 2019. That's as far as I've got for Yaima for 2019. I just want to move on to what we were doing for the Icequakes volcano. So just to give you an idea of how close these volcanoes are to each other, these photos are actually photos of each volcano taken from the slope of the other volcano. So for example, this is a photo of the Eureka from Yaima. So the Eureka volcano is probably quite well known to a lot of people watching this talk. It's one of the few volcanoes around the world that hosts at least a semi-persistent lava lake at the summit. And this lava lake is accompanied by very frequent low-level storm boiling explosions. But sometimes this can really escalate into quite major eruptions, such as this one in 2015, where you see at least a 2-kilometer high lava fountain, which generated lahars. They're quite fast-moving lahars that move towards residential areas. There's at least 16 square kilometers of glacial ice present on this volcano, and it's also an extremely popular tourist region with the national parks and lakes. So people, and I think there's something like 15,000 people climbing to the summit of this volcano each year. So again, Icequakes are very rarely catalogued by OVDAS here. But the question for this particular volcano is, because it is so active with this lava lake, are the Icequakes being obscured by the volcanic activity, or are they actually being mixed up by in the volcanic events that are catalogued for this volcano? So this is what we deployed in January early this year. So we did another network plus array configuration. And together with some colleagues from Boise State, we deployed at least 45 sensors. I should also add, I had a lot of help from Christian Farias from Universidad Católica in Temuco. And together with them, we deployed at least 45 sensors across 21 locations around the volcano, including broadband and short period seismometers, as well as infrasound microphones. Some of these short period seismometers are actually some low cost off the shelf sensors. So these Raspberry shaken booms. And I was testing, hoping to see how effective these might be for volcano monitoring. So now the original plan was to actually retrieve these instruments in April, but unfortunately I wasn't able to go down to Chile because of the coronavirus crisis. So currently these stations are buried under several meters of snow. So I'll probably go back to the volcano in December and January after the snow is melted, and hopefully not too many of the stations are going to be damaged by the snow. So by now, I was hoping I'd be able to present like a really nice, massive seismic and acoustic data set. So for the next couple of slides, I'm going to present, what I'm going to do is present some work I've been doing elsewhere in the world in Alaska. But actually, before I get to that, I just want to give you now a taster of what we might see in the seismic and acoustic data set from Villarrica. So this is from some seismic and acoustic data I was able to recover from this station before I finished the deployment in January. So this is a seismic and acoustic event that with no acoustic waveform. So is this a glacier or volcanic event? It's not really clear for this particular event, but we can also see some nice examples of explosions where we see a seismic waveform shortly followed by an acoustic waveform. So this is just to give you an idea of what we might hope to see in a much larger data set when I do eventually get to recover those stations. So just instead of covering Villarrica in detail, I'm just going to show you what I've been doing in Spur volcano in Alaska. So just to give you a quick rundown of this volcano, this is the easternmost active volcano in the Aleutian Arc, one of the closest volcanoes to Anchorage. It had a major eruptive period in 1992 with a 15-kilometer high ash plume with a lot of disruption to the Anchorage International Airport, which is a major freight hub for between the Eastern Asia and Northern America. And I'd actually like to extend special thanks to Mike West at the Alaskan Earthquake Center, who brought my attention to this quite interesting seismic activity at Spur in the past 10 years. One of which was in 2016, where he himself had to write an article reassuring the public that what they were seeing at Spur volcano was not a volcanic seismic storm, it's more likely to be something glacial. So Mike suggested I look into this in a bit more detail. So I have been able to find some time to look at some of the data that's available on IRIS and the USGS Earthquake Catalog. So I followed a very similar workflow to what I've been doing at YAIMA, but instead, because I'm looking at multiple years of data, I used the RedPy algorithm that was developed by Alicia Hotovec-Ellis, which is much more capable at looking at multiple years of data very quickly. What we can see here is that I plotted the total events per month of repeating events versus non-repeating events. And you can see there's actually at least 5 periods where you can see quite intense repeating activity. And these are not really an annual event. So there's at least 2 years between these events. So this is not something that's related to seasonal activity. It's probably something, maybe some surge glacial activity. I'm not really entirely sure. And there's not really any obvious relation with snow depths or temperatures. So in this plot here, I've got some snow and temperature from the ERA 5 data. And the only hint of this is that before this big spur in repeating seismic activity in 2016, you can actually see some of the highest calculated snow levels in the winter before. So this is hinting that maybe it's something to do with the level of snow in the area before these ice quakes might be occurring. Because many of these events have been also catalogued by the USGS, I've also been able to plot their locations around Spur. So this is actually where the Spur volcano is. This is the location of the event in 1992. And you can see that 3 of the largest families for the past 10 years are plotted in the same location that Mike West had noted in his article in 2016. There's also 2 other families of events, one in the north, and there's a lot of glaciers in this area as well. These are probably icequakes too. And there's also another interesting one here, directly beneath the volcano. And I should add that the volcano itself is covering a lot of glaciers. So the question remains is, are these volcanic or are they actually something to do with the glacier itself? I'm also proposing to do some work in Iceland. I'm particularly interested in looking at Grímsvötn volcano, the most active volcano in Iceland, and Árfjallajökull volcano. This particular volcano has produced some of the largest eruptions in Iceland. It also had an eruptive crisis, a seismic crisis from 2016 to 2018, which was thought to be due to an intrusion beneath the volcano. And as you can see in this plot here, what I've done is I've taken or the Icelandic Met Office seismic events that were less than 3 kilometers depth beneath the volcano for the last year. And you can see that there's quite a lot of seismic activity at these volcanoes. And it's not really clear whether there's something to do with the volcano or something to do with the glaciers that are on these volcanoes. So this is just a quick list of what I would do in the future. So obviously I'm going to recover and analyze data from the volcano, like I said before. I'm going to go into a bit more detail in Spur volcano in America and these particular volcanoes in Iceland. And ultimately, I would like to try and develop some kind of algorithm for automatically classifying these icequakes. So I wouldn't have got this far without the great help from a lot of people around the world. I'd like to extend special thanks to Luis Franco and Jonathan Lazzo at OVDAS in Chile. Also, extend special thanks to Jonathan Lees, Stephen Lee and Michael Shaw in Chapel Hill for their help in getting this project as far as it has. I'd also like to spend special thanks to all the students that have helped me from Chapel Hill and Boise State in deploying the seismometers and microphones at Yaima and Villarrica in the past couple of years. So this is the last slide of my talk. These are just the key takeaway points I'd like you to take away from this talk. And I think the key point is that the potential icequakes are very frequently seen in the seismic records of Yaima volcano. And some of the locations suggest that the active sources are most likely some basal slip beneath the glaciers, quite surrounding the volcano summit. Thank you very much, and I'm happy to answer any questions you may have.
Thank you, Oliver. That was great. As people formulate some questions, you can just use the raise the hand function. I see we have 2 questions already, though, that came up during the talk. And the first is from Josh Crozier. And so this is related to the first half of the talk, roughly. And he writes, is the division of earthquakes into 11 families robust, or would more or less families be found with slightly different correlation thresholds? So I guess he's asking, how are the thresholds set?
So the threshold that I used for the families is relatively low. So I used a 0.7 threshold. So this is so for those of you who are not familiar with cross correlation, when you're trying to divide into families, you set cross correlation. You find cross correlation numbers between 0 and 1, where 1 is they're completely identical, and 0 is they're not identical at all. So I set a threshold of 0.7, and this is slightly lower than what was used at, for example, Mount Rainier. And the reason I did this was because a lot of the earthquakes that we're seeing at Yaima are incredibly low magnitude, and also is that there's a lot of noise. So I really wanted to try and just to expand the scope of what we were seeing. So I did try with different correlation thresholds, and basically, unsurprisingly, if you set the threshold higher, you find less families. If you set the threshold lower, you find more families. But if you set the threshold too low, you run the risk of putting a lot of useless families in there that are just nothing to do with icequake or volcanic activity in there. Or if you set it too high, you run the risk of missing a lot of events. So it's kind of like just tuning it to just to be. It's kind of like hit and miss. There's no real way of getting an accurate threshold for this.
Thanks, and I should add that feel free to jump in, other folks, if you want further information or want to add something. So the next question is from Mario Ruiz, and he asks, "What is the maximum magnitude of icequakes that you've recorded in Chilean volcanoes?"
That's a great question. That's something I'm going to work on in the next few months. But I would sort of estimate that they're extremely small. I could probably no more than 1 for Yaima. But it's interesting to note that some of the icequakes that have been seen in places like Katla and in Rainier are a little bit higher, so maybe on the order of magnitude 2 or 3.
There's another question from Josh Crozier. Have you tried any other non-correlation based means for clustering earthquakes in any of the data sets?
No, I haven't, no. Although I would be very open to any kind of ideas for non-correlation ways of clustering the earthquakes. So I'd be very interested to hear what other people have been doing with non-correlation means.
Yeah, we might, if Josh wants to stick around towards the end of this talk, we can always maybe chat a bit more too. This is a question from Ben Andrews. Ben writes, do you see, or would you expect to see, seasonal changes in the types or numbers of ice quakes? And are there correlations with the local weather? So,
That's a fantastic question. It's a very quick. So unfortunately, the data sets I'm looking at from GAIMA are not really long enough to look at seasonal changes, but I would definitely expect to see seasonal changes. And the reason I say that is because all the other studies, especially Katla and Rainier, where they looked over 10 years of data, they've seen extremely strong seasonal changes. And you're quite right to say that they are very strongly correlated with local weather. What's interesting to note is that both of these studies actually saw different correlations. So Katla, they see very strong correlation with the time of year when they see a lot of melting at the volcano. So that's sort of the August, September time of year. But then at Mount Rainier, what they see is actually they see a much stronger number of potential of ice quakes in the time of year where there's a lot of snowfall. So it's kind of interesting to see that there's actually different ways of seeing these seasonal changes in ice quakes at volcanoes.
Okay, great. Other questions out there? Well, I have one question, I guess, that well, maybe people are formulating other questions, and that is, I was wondering if you could comment a little bit more, it kind of relates to what you just said, but which is distinguishing meltwater migration events versus slip events. I mean, are these fairly easy to distinguish with instrumentation? The contrast between the two, or is location give you some clue about the type of event?
So just to clarify, you're asking whether it's easy to differentiate between melting ice quakes and stick slip ice quakes.
That's right, yeah.
Okay. Yeah, it's not too easy. The most important thing you would need is a station that's really close to the glaciers. And the reason I say that is one thing they noticed is that high frequency ice quakes, so those that might be associated with stick slip, they tend to attenuate very quickly because they're happening at the surface. So then they change into these low frequency earthquakes very quickly as they're moving away from the source. But if you're looking at something to do with meltwater movement, then you might expect to see just low frequency. You wouldn't expect to see too much high frequency earthquakes in there. So it's difficult. It really depends on how close the closest station is to the source.
Okay. That's great. Other questions out there? Well, thanks again, Oliver. This is wonderful. What we might probably do here, because usually there are people that have little questions they want to bring up at the very end. What we might do is just close out here. And if you do have little questions and you want to, have the equivalent experience of walking up to the podium and asking Oliver a question, then Oliver maybe can stick around for a couple minutes. But thanks, everyone. And please join us again next week for the Lindsay seminar. Thanks again.
Yeah.
And Oliver, I was just going to note that the comments and everything are recorded too. So if you want to take a look at them later, you can also have a record of that. I know it's hard to do lots of things at once when you're giving a talk. That was really great. That was fantastic.
Yeah. I think Diana has a question.
Oh, yes.
Hi, Oliver. Can you hear me?
Yes, I can hear you. Thank you.
Okay. Just great talk. I just been meaning to check in with you, but wanted to say right now we're hoping to go down in November. So we'd still love to coordinate with you and on the salvage mission and still love to share data. I think,
okay.
Obviously we got a lot of snow and we'll see what there is, but please keep in touch with us.
Absolutely. Yeah. Thanks, Diana.
Elephants. You have to say something about these acoustic measurements of elephants on your website.
Yes, so yeah, it's one of my colleagues at Chapel Hill is involved with testing various geophysical instruments with recording, tracking elephants in the wild. And he just said, "Oh, Oliver, you have all these instruments. Why don't you come to South Africa with me and test how well your sensors work with the elephants?" So I went down to South Africa last October and we recorded some elephant noises and some movements. So we have a paper in review right now that's sort of documenting some of the work we've done with that. So yeah, keep an eye out for that.
That's great.
I'd like to see you put some elephant waveforms on John Power's volcano seismicity schematic.
Say that again.
Put the John Power, the USGS volcano seismicity schematic that shows VT events, tornadoes, LP events. You should add a elephant waveform.
Yeah, I should. Yeah, just in the bottom. Absolutely, it's a great idea.
Josh, did you have something you wanted to mention too, or chat about?
Yeah, I was just going to follow up on the non-correlation based means of clustering earthquakes. And so one of those, you might have heard about it, is called FAST, like capital F-A-S-T. But the basic idea with these things is, in particular, if you're looking at fluid resonance type events, you might have what would essentially be the same resonant mechanism or the same family of seismicity, that events within that family wouldn't actually correlate very well with each other if they have slightly different resonant periods. For example, if, let's say it's some meltwater channel in an ice sheet, if that's gotten wider or narrower or something, you change the frequency. And so sometimes if instead of just correlating events, you come up with other traits of events, which can be either very abstract things that some machine learning algorithm picks out, or they can be more based on the frequency spectra, et cetera.
Okay, yeah, actually that's sort of starting to, I'm starting to remember something like that, and I'm glad you reminded me about that. That's great, thank you.
Yeah, I would look up, the one called FAST is the one that comes to mind that people have put some work into.
Okay, thank you, appreciate it.
Actually, Oliver, on a related question, when you are doing the correlation way of grouping waveforms, I could imagine a case where you have 3 waveforms, 2 of which are very different from each other or significantly different from each other, but the third waveform has a 0.7 correlation with both of the others.
Yeah.
Does that ever happen? And if so, how do you group things? Is it is there a clustering analysis or something like that?
Yeah, so we use the hierarchical clustering analysis, and essentially you just choose the correlation which is higher. Okay. So yeah. So what you might find, something like that, is that if you sort of lower the threshold, then all 3 events might put into the same family. But if you increase that threshold, then they might be separated into 2 families.
All right, well, excellent. Oliver, thanks again. I'll be sending an email a bit later on, but this was fantastic. Great to hear about all of your work.
Appreciate it. Thanks for the invite.
Cheers. Well, I guess I'll see everybody next week, and see you, Josh, later this afternoon, I guess. So.
Okay. I did actually have one last quick question.
Oh, yeah, one last. Okay,
yeah. Are there very good models, or at least understanding from data of what we would expect things like crevasse opening events on glaciers and stuff to look like in infrasound?
Sorry, can you repeat that?
Do we understand very well what the icefall or crevasse opening events should look like in infrasound data?
So there's been a little bit of work in the Alps where they've done some infrasound work on looking at icefall events, and actually they kind of look like mini explosions. So sort of all this chunk of ice hitting the ground, and it looks like sort of explosions. But I think you have a slightly longer tapering end as all these infrasound is bouncing off the walls of where the glacier is. So yeah, there's been a little bit of work. There's exactly that. I'm not sure about crevassing. I'll have to check that, but I know that there's been a lot of work done on icefall in the Alps. Okay.
great. Thanks again. This was wonderful.
Thanks.
Thanks for a nice presentation.
Cheers. Well, I guess we'll catch you a bit later down the road, Oliver. Thanks again, and wonderful work. I'll be looking out for those papers in even the African elephant paper. That'd be great. All right, take care.
Thanks. Yeah. This is a great seminar series. It's been great. So.